In this video, we're going to look at the definition of a function and some examples. A function is a rule that assigns exactly one output to each input. Here's an example where we have a set of input values. This set is called the domain, and a set of output values. This set is called the range. A function will take each of these input values and assign it or map it to exactly one of these output values. So let's make up a function here. We'll start with the input 0. Let's say we assign this input to the output 5. In this type of example, we can illustrate the assignment or the mapping with an arrow. Next, for the input 3, let's assign this to the output 2. And for the input 5, we'll go ahead and map that to the output of 6. So here we have a function. Each input is assigned or mapped to exactly one output. Let's name this function f. We'll typically use letters like f and g and h to represent functions. This type of diagram is useful for illustrating how each input is mapped or assigned to a specific output value. More typically, a function like this would be represented as a table or a collection of ordered pairs. Here, we put the input values in the first column and the corresponding output values in the second column. The input 0 is assigned to the output of 5. The input 3 is assigned to the output 2. And the input 5 is assigned to the output 6. So in this table, we have the same information that we have in this diagram. We'll often list these as ordered pairs. Then they can be graphed so you can get a visual image of your function. In this case, the input value will always be the x-coordinate and the output value will always be the y-coordinate. So we get the ordered pairs 0, 5, 3, 2, and 5, 6. So again, this gives us the same information about the function that we get from the table and from the original diagram. The ordered pairs are primarily used if you're going to graph the function. If you just want to list the inputs and the corresponding outputs, you would probably use a table. There's one other notation that we use for functions, and that's called function notation. We named this function f, and so we want to say that f takes the input 0 and maps it to the output of 5. We start with the name of the function f with a set of parentheses next to it, and we'll put the input inside the parentheses. So let's start with the input of 0. In this notation, the parentheses do not mean that we're multiplying. This is not f times 0. This is read as f of 0. And when we say f of 0, we mean the output that f assigns to the input of 0. And we can see here that the output assigned to 0 is 5. So f of 0 is equal to 5. We can make a similar statement for the remaining inputs. We get f of 3 is equal to 2, and f of 5 is equal to 6. Each of these different representations defines this function f by specifying the assignment of each input to exactly one output. Here's the example that we just looked at. Let me remind you that the only condition we need for this to be a function is that each input is assigned to exactly one output. That means in a diagram like this, you can have exactly one arrow coming from each input. And here we assigned a different output to each input. But you could assign two inputs to the same output. For example, we could have the input 0 and the input 5 both assigned or mapped to the output of 5. This would still satisfy the definition of a function, because each input is mapped to exactly one output. If this were our function, we would not include the value 6 in our range, because the range only consists of the output values, and now 6 is no longer an output. So even though we have two arrows or two inputs being mapped to the same output, this is still a function, because if I give you any one of these inputs, you can tell me the corresponding output. Let's call this function g, since it's different now from the first example. If I ask you, what is the output assigned to the input 0? Or what is g of 0? You follow the arrow, and we see that the output is 5. If you're asked for the output corresponding to the input of 3, you can see that g of 3 is equal to 2. And what is the output corresponding to the input of 5? That would be the output 5. So if there's no question about which output is assigned to each input, then this represents a function. This satisfies the definition that there is exactly one output for each input, and that makes this a function. Let's compare this to an example that's not a function. We'll call this mapping H. And even though I'm going to show that this is not a function, it still defines a correspondence between the set of values in the domain and the set of values in the range. And any correspondence like this is called a relation. Any pairing of values from one set with values from another set is a relation, but to be a function, the values from the first set can only be paired with one value from the second set. Relations that are not functions can still be useful and still have applications, but we make the distinction because when we study these in algebra and calculus, there are certain properties that will only apply to functions. Let's look at why h does not represent a function. You can probably already see this based on what we've said so far. If I were to ask you what output corresponds to the input of 2, or what is h of 2, we won't be able to get a single answer for this. We'll have two choices. 2 corresponds to the value of 5, and it corresponds to the value of 6. And that violates the definition of a function. A function can only have one output for each input. In the homework, you'll be given examples of relations, and you'll be asked to state the values from the domain and the values from the range, and then you'll be asked if the relation is a function. You probably won't see many diagrams like these. These are useful for illustrating the concept of a function. But typically, when you're given a relation, it will be given as a set of paired values, either in a table or in a collection of ordered pairs. Let's write the ordered pairs for each of these two relations and see how to determine whether the collection of ordered pairs represents a function. For G, we get the ordered pairs 0, 5, 3, 2, and 5, 5. For H, we get the ordered pairs 1, 4, 2, 5, 2, 6, and 3, 6. If we started with these ordered pairs, and we were asked to state the domain and range, the domain would be the set of x coordinates. So for G, the domain is 0, 3, and 5, the x coordinates from these ordered pairs. And for H, the domain is 1, 2, and 3, the x coordinates from these ordered pairs. We do not need to repeat the value of 2. This is just one value from the domain. For the range, we list the y-coordinates from each of these ordered pairs. The range for G has the numbers 5 and 2, and again, we do not need to repeat a value if it shows up in two ordered pairs. And the range for H are the values 4, 5, and 6, the y-coordinates from these ordered pairs. Now, if we're asked whether or not these collections of ordered pairs represent a function, we want to see if there's exactly one y-coordinate for each x-coordinate. That means if this collection of ordered pairs represents a function, then each of the values from the domain should only appear in one ordered pair. If each ordered pair has a different x-coordinate, that means that each input or x-coordinate is assigned to exactly one y-coordinate or one output. So G represents a function, but H does not, because the x-coordinate of 2 shows up in two separate ordered pairs, and that means it's assigned to two different values from the range. If we plot these ordered pairs in a coordinate system to form a graph, then there's a graphical test that we can use to determine if this represents a function. Remember, we plot the x-coordinates on the horizontal axis and the y-coordinates on the vertical axis. The ordered pairs 0, 5 will have an x-coordinate of 0 and a y-coordinate of 5. The ordered pair 3, 2 has an x-coordinate of 3 and a y-coordinate of 2. And 5, 5 has an x-coordinate of 5 and a y-coordinate of 5. Now I'll plot the ordered pairs for H. So here's the ordered pair 1, 4 with an x-coordinate of 1 and a y-coordinate of 4. 2, 5 has an x-coordinate of 2, y-coordinate of 5. 2, 6, x-coordinate of 2 and a y-coordinate of 6. And 3, 6. Remember, the ordered pairs that made this not a function were the two ordered pairs with the same x-coordinate and different y-coordinates. Those are the 2 points here, 2, 5 and 2, 6. If you have two ordered pairs with the same x-coordinate, they're going to fall on a vertical line. Any graph that has two or more ordered pairs on the same vertical line will not be a function. For the graph of a function, any vertical line will have at most one point of the graph on that line. This is called the vertical line test. So the vertical line test says that if every vertical line intersects a graph at most one time, then the graph represents a function. That's what we have here in the first case. This graph only consists of 3 points, but every vertical line that we can draw in this coordinate system will intersect this graph at most one time. This is equivalent to saying that each input value of x corresponds to exactly one output value of y. If any vertical line intersects a graph at more than one point, then the graph is not a function. That's because on this vertical line, we have the same x-coordinate or the same input values, but we have two different outputs or two different y-coordinates. These are not very interesting graphs because they just have a small collection of ordered pairs. Most of the graphs that we'll be looking at will be lines or curves, but the vertical line test will still apply. In the next video, we'll look at some examples of these.